Hello, this is Miss Moore, and today during chemistry we're going to discuss LewisDot structures. Today's essential question: how are LewisDot structures used to show covalent bonding? It's really important today that besides writing down the words, that you actually write down and participate in all the practice problems. Those are a really important part of your learning. Okay, so let's get started with what is a covalent or molecular bond? Well, a covalent bond or a covalent compound, are formed when elements share electrons. So the bond in which electrons are shared between two atoms is known as a covalent bond. So these two atoms will share an electron, which actually ends up hooking the atoms together because they're both holding on to the same thing. And then very important, because we're going to learn about different types of bonds later, is that covalent bonds are formed between two non-metal atoms, two or more non-metal atoms. So real quick, if you remember, the non-metals are the metals on the jaggedy line here. They're everything to the right, okay? So all of these right here can form covalent bonds with each other. All right. So next is the types of covalent bonds. So there are a covalent bond known as a single bond. In a single bond, two atoms share one pair of electrons, and that means 2 electrons total. Because a pair is 2, like a pair of shoes. And it's 1 electron from each atom. I know this probably sounds really weird, but when I actually show you the bonding, it'll make more sense. So for right now, we're kind of going through the definitions. All right, so we have a single bond, which shares 1 pair of electrons, or 2 electrons total, 1 from each atom. Next, we have a double bond. A double bond is a bond in which 2 atoms share 2 pairs of electrons between them, which means 2 pairs. 1 pair is 2 electrons. So this time we have 2 pairs, which means 4 electrons total. Or 2 electrons from each atom. And one more type, I bet you can guess. It would be a triple bond. Before I show the definition, think it through. If a single bond shares 1 pair of electrons, or 2 electrons total, if a double bond shares 2 electrons, 2 pairs of electrons, 4 electrons total, a triple bond would is a bond in which 2 atoms share 3 pairs of electrons, or 6 electrons total. Which means 3 electrons from each atom. All right, so we have single bonds, double bonds, triple bonds. 1 pair of electrons, 2 pairs of electrons, 3 pairs of electrons. So on to LewisDot structures. LewisDot structures are used to determine the number of electrons shared in a covalent bond. And as chemists, we really like the outermost electrons, the valence electrons, because those are the electrons involved in bonding. Whether we're talking about ionic or covalent bonding, we haven't gotten to ionic bonding yet, that's okay. Remember, valence electrons are the electrons in the outermost energy level. And a LewisDot structure represents the valence electrons in a molecule. So we're going to spend the rest of the lecture talking about LewisDot structures. We'll first talk about the LewisDot structure of an atom, which is really figuring out its valence electrons. And then we will learn how to put those atoms together to make a covalent bond using LewisDot structures. Let's do this. How to draw Lewis electron dot structures for a single atom. We're going to do a practice problem while we're going through this. So let's see. We're going to first write the atom symbol, but I guess I need to come up with a practice problem. How about, oxygen's a good one. Let's use oxygen. Okay. So the first thing we do is we draw the atom symbol for oxygen. So let's go back to our periodic table real quick. Clean this up. And let's find oxygen. There's oxygen, and his symbol is an O. So I will write an O here. That was easy. Now we need to determine the number of valence electrons. The correct way to figure out the number of valence electrons is to look at the orbital diagram or the electron configuration. So we see how many electrons oxygen has, which is 8. So I would write 1s2, 2s2, 2p4. And then we look at the electrons in the outermost energy level, which the outermost energy level is 2. So 2, 4, we have 6 valence electrons. And that's the right way, I guess, to figure out number of valence electrons, to at least understand them. But I'd like to now remind you of an easier way to do that. And that's just to look at the atom's location on the periodic table. So all the atoms in group 1 or 1A, which means hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they all end in, S1, which means they have 1 valence electron. Everything in group 2 or 2A end in S2, which means they all have 2 valence electrons. The transition metals here, I'm going to just cross them out for now because their valence, they end in the D block, if you remember, which means they'll never end up. The D's will never end up being valence. We'll get back to that later. Let's just jump over to the P block. Group 3A or 13 all end in S2P1, meaning how many valence electrons do they have? 3. Group 4A or 14 all end in S2P2, which means they have 4 valence electrons. Group 15 or 5A all end in S2P3. So they all have 5 valence electrons. I'm going to zoom in a little bit here. Everything in group 16 or 6A all end in S2P4. So they have 6 valence electrons. Everything in group 17 or 7A end in S2P5, so they have 7 valence electrons. And lastly, everything in group 18 or 8A end in S2P6, almost everything, meaning they have 8 valence electrons. Helium is the exception. Helium only has 2 valence electrons because he only has 2 electrons total. So if you look at the overall pattern here, everything in group 1 it has 1 valence electron. Everything in group 2 has 2 valence electrons. Everything in group 3A has 3. Group 4A has 4. Group 5A has 5. Group 6A has 6. Everything in group 7A has 7. And most in group 8A have 8. So if you know the location of the atom, you know how many valence electrons there are. So oxygen is in group in group 6A, which means it has 6 valence electrons. So, which is what we figured out before. Okay, so we've written a symbol. We know the number of valence electrons. The next thing we need to do is write the valence electrons as dots around the atom symbol. And let me just put this part in and then we'll go back and do that. So remember that only the s and p orbitals can be valence electrons, so there are only possible 4 orbitals for valence electrons. And they're arranged around the atom. So I'm going to zoom in for a minute. So if I have the atom oxygen, its valence electrons, think of these as invisible orbitals. So we have a total of 4 for the s and p. And just like when we were doing orbital diagrams, you only put 1 electron in each orbital first, and then you go back and fill in, you double them up. So if you remember, we had a total of 6 valence electrons. So I'm going to put 1 in each orbital. And then wait, before that, it doesn't matter where you start. Okay, I started at the left side, but I could have also started top, bottom, side. It doesn't really matter. Okay, and then I need to add 2 more, and I can double them up, and I can do it wherever I want. I'll put 1 on the left side and 1 on the top, but I also could have put 1 on the left side, 1 on the right side. I could have put 1 on the top or 1 on the bottom. That part doesn't really matter. Okay, so that's sort of what a LewisDot structure for a single atom would look like, except for we don't normally write what I drew, those orange boxes. Those are supposed to be invisible. So the way I would really write this is like that. So there is the LewisDot structure for an oxygen atom. Now let's do, each side of the atom represents 1 orbital. I kind of already showed you that up there. So that's the stuff I drew in orange. Okay, so I want to go through one more example really quickly and give you a little bit of terminology, which we'll come back to in a little bit. It'd be awesome if I could spell. Okay, so an example with some terminology. So let's try phosphorus. So I've already drawn the atom symbol. The next step, let's go back and look, step 2 is to determine the number of valence electrons. So let's find the location of phosphorus. Phosphorus is right here in group 5, which means it has 5 valence electrons. So phosphorus has 5 valence electrons. So we're going to put 1 electron in each of the invisible orbitals. So we have 1, 2, 3, 4. So now we've got 1 in each spot, and we can double 1 up. It doesn't matter where you put it. I'm going to go ahead and put it at the top. Okay, so there is the LewisDot structure for phosphorus. Now a little bit of terminology, and there'll be more later. So the single ones that I'm circling here are known as bonding electrons. anything that's single can bond. So this particular phosphorus has 3 bonding electrons. Well, actually all phosphorus do. The paired up ones have a lot of names, but they are non-bonding electrons. They can also be called lone pairs. Okay, and it's very important that you know this as we move on to LewisDot structure, because the bonding electrons are going to be the ones that do the bonding. So we really need to know what those are. So now let's draw structures for covalent compounds. I guess put these both up. So how to draw LewisDot structures for covalent compounds. So the first step is to draw the LewisDot structure for each atom in the compound. So let's do a practice problem while we're doing this, and I will pick O, because we just did that one, F2. So O, and then list out F2 means there's 2 of them, right? So we have OF2. All right. We'll start with oxygen. Oxygen, again, boy, this is a mess. Get rid of this stuff. Oxygen is located in group 6A, meaning it has 6 valence electrons. So 1, 2, 3, 4. I can go back and double up. This time I'll make it different. I'll put 1 on the top and 1 on the side. 1, 2, 3, 4, 5, 6. All right, how about fluorine? Fluorine is here, located in group 7A, meaning it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. So we did step 1. Now step 2, what we want to do now is bond these together. So step 2 is to start with the atom that has the most bonding electrons. And remember, the bonding electrons are the electrons that are by themselves. So let's, I'm going to go through and color my bonding electrons green. So oxygen has 2 and fluorine has 1. So who has the most bonding electrons? Well, oxygen does. So let's start with him. We have oxygen, and usually put him in the middle. I'm just going to redraw him. And oops, right there. All right, so I'm going to cross him off our list. We've used that one. All right, the next thing you want to do is select the atoms with the next most number of bonding electrons to bond with the first atom selected. So, well, fluorines are the same, so let's pick one of the fluorines. Here's the thing, though. Let me draw my fluorine. I'll draw them right here. Fluorine. Now what can happen is that the 2 green ones can bond. Problem is they're not really near each other, which is not a big deal. We drew the electrons, however. So what I'm going to do is I'm just going to change. I'm going to move the bonding electron to the side and put the lone pairs at the bottom. Okay, we still have the same number of electrons. And then these 2 can bond right there. Okay, they've bonded together. Continue steps 2 and 3 until all of the atoms have been used. So we've used 1 fluorine. We have 1 more fluorine to go. So let's put the other fluorine on the other side, and I'm going to draw them just the same. And we want to bond this one and this one, but they're not near each other, so I will just move them. I'll just move this. I'll put the lone one on the left or on the right, sorry, and the lone pairs on the left. Now the 2 bonding electrons can bond. So real quick, you first draw the LewisDot structures for each atom in the compound, which we did. We started with the atom that has the most bonding electrons, the most lone single electrons. That was oxygen. We selected the atom with the next most number of bonding electrons to bond with the first atom selected, and in this case that was fluorine. The fluorines were the same actually. Connect a bonding electron from each atom. The 2 green ones, we did that. All right, we continued steps 2 and 3 until all the atoms were used up. And we ended up with that, and all of the bonding electrons are bonded. That's really, really important. You want all bonding electrons to be bonded. So let's make sure we got that put in there. All right. Okay. Let's move on. If an atom contains unused bonding electrons, you can make a double or triple bond, which means you can share 2 or 3 pairs of electrons. And I will show you that in a moment. So atoms can share more than 1 bonding electron. When you're all the way done, change each pair of dots that represent a shared pair of electrons to a single dash. So, if you remember, we called the green ones bonding electrons. But once they've been bonded, we change their name. So I'll draw that in pink here. Instead of being called bonding electrons now, they're now called shared pairs. And the white ones are still called, like all of these, lone pairs. So when the green dots are alone, they're called bonding electrons. Once they've shared with another atom, once they've been bonded up, we now change the name to shared pairs. Okay, so the last step, again, let's go back to that real quick, was change each pair of dots that represent a shared pair of electrons to a single dash. So the way you would rewrite that structure is, I'll do it down here. The final answer would be F bonded to an O, bonded to an F. So we took out the bonding electrons and put in the shared pairs. So 1 dash equals 1 shared pair. And that'll be important later. I want to go through real quick a list of terminology, most of which I kind of already went over, but just to be on the safe side, and that you have everything down, and then we'll do one more practice problem. So a bonding electron is a single unpaired electron. So example, let's go to just use that F again. That green one is a bonding electron. Unshared electrons are electrons that are not shared with another atom, also known as, so unshared electrons are also known as lone pairs. And in my F example, the unshared electrons are the white ones. Unshared pair of electrons are a pair of electrons not shared with another atom, so two. Shared pairs of electrons are electrons that are shared between two atoms. So an example of a shared pair, let's put our example back. So this is a shared pair, the pink one, and a bond is another way of saying a shared pair. Okay, so I want to try one more practice problem, or maybe two, and then that'll be it. Please don't skip these practice problems. All right, so we're going to draw the LewisDot structure for C2H4. So the first step is to draw the LewisDot structure for all the atoms in the molecule. So we have C, H, ooh, too much space there. H. All right, so let's see how many valence electrons carbon has. That's the C. So carbon is right here in group 4A, which means 4 valence electrons. 1, 2, 3, 4. None of them are paired up, which means they are all bonding electrons. So let's change that to green. And that'll be the same with the second carbon. All right, hydrogen is located in group 1A, which means 1 valence electron. They are also bonding electrons. Okay. All right. Next step is start with the atom that has the most bonding electrons, which in this case would be the carbon. And there are, so carbon, so use this one. Now we have another carbon. It has the most bonding electrons. So we'll put him right with the first carbon. And let's share them. All right. Now we need to go to the next, which is hydrogen, all of the hydrogens. So each of the carbons has, well, back up, Miss Moore. You want to bond the things up here with the atom that has the most bonding electrons, which carbon and carbon have the same number right now. They each have 3. So I'm going to go ahead and put this hydrogen on the left. And they can bond up. Now we have another hydrogen. But the carbon on the left only has 2 bonding electrons, where the carbon on the right has 3. So the next the next hydrogen needs to go on the right side carbon. Okay, you want to bond to the atom that has the most bonding electrons. So I'm going to put the H here, and I'm going to just go ahead and move this valence electron to the other side. So I can bond those up. All right. Now each carbon has 2 available bonding electrons. So the next hydrogen can go wherever. I'm going to go ahead and put him on the left carbon. And I moved his valence electron up to the top. And we'll bond those up. And one more carbon left. The carbon on the left only has 1 bonding electron, where the carbon on the right has 2. So the last hydrogen needs to go on the carbon on the right that has more bonding electrons available. All right. So we've now used all our atoms, but we have not used all of our bonding electrons. We still have these left. So let's go back to our notes real quick. If atom contains any unused bonding electrons, you can make a double or a triple bond. Atoms can share more than 1 bonding electron. Remember that we have to use all the bonding electrons. So we can bond those. Now we've used all the bonding electrons. So the last step is to rewrite this mess nice and neat. So what I'm going to do is I'm going to write hydrogen, carbon, carbon, hydrogen, hydrogen, hydrogen. And I'm going to take, well, I'll just put it here. This shows 2 pairs that we call, that's now our double bond. So I just took this big one here, kind of shrunk it down to make it look neater. And I hope you feel okay about that. That's it for today. Have a good one.